Hi everyone, I'm Sapida Maliki, and today I want to talk about our research Bipart, which is a parallel and deterministic hypergraph partitioner. This is a joint work with Udit Agarwal, Martin Bercher, and Keshav Pingali. Please feel free to interrupt me during this talk if you have any questions. So what is a hypergraph? A graph is a set of nodes and a set of edges where an edge can connect two nodes. A hypergraph is a generalization of a graph where an edge or a hyperedge can connect any number of nodes. For example, on this figure on the right, we have a hypergraph, and a red circle is a hyperedge that is connecting nodes A, C, and E. We can represent a hypergraph by bipartite graph where we have two sets of nodes. One set of nodes is our hyperedges in the original hypergraph, and another set of nodes is our nodes in our hypergraph. And there's an edge between these two sets if that nodes belong to that hyperedge. For example, on the left, we have a hypergraph, and hyperedge 3 is connecting node A, C, and E. Similarly, on the right, the bipartite representation has node 3, which is connected to A, C, and E because these nodes are in hyperedge 3. So in this work, we are interested in hypergraph partitioning. A hypergraph bipartition is to partition nodes of a hypergraph into two sets, where the number of nodes in each set is roughly the same. We are interested to minimize the total cut in this problem. And a cut is basically we want to minimize the number of hyperedges connecting nodes in different partitions. For example, on the left, we have a graph. This graph has two partitions divided by this gray line, and all these edges are cuts because they have nodes in both partitions. On the right, we have a hypergraph. This hypergraph also has two partitions, blue and the green, and hyperedges H1 and H2 are cuts because they have nodes in both partitions. There are many applications for hypergraph partitioning, from load balancing in parallel processing, where data are vertices of a hypergraph and hyperedges are dependencies between data. In VLSI physical design, a circuit can be represented as a hypergraph, and finally, in numerical linear algebra, matrices can be represented as hypergraphs. And there are many other applications. In some of these applications, it is important to have a deterministic hypergraph partitioning. For example, in VLSI physical design, we use graph partitioning to partition hypergraph partitioning to partition a circuit. And then this algorithm is followed by a placement algorithm. A placement algorithm has to be deterministic. This is why we have to make sure that our hypergraph partitioning is also deterministic. There are two ways to get Kv partitioning. One is to do a recursive bisection, and another way is to directly create K partitions. In Bipart, we use a recursive bisection. It is also important to mention that a Kv partitioning is NP-complete, so all the algorithms are basically just heuristics. There are various approaches to partitioning. One is topology-based method, which we use a node connectivity to do the partitioning. An example for this method can be BFS. We have geometry-based method where our nodes of the graph are points in RD, and we use this information to do the partitioning. K-means algorithm is an example of this technique. We have embedding-based methods where we map nodes of our graph to points in RD, and we use that information to do the partitioning. A spectral partitioning is an example for this method. And finally, we have optimization techniques for partitioning, and multi-level partitioning can be an example for this optimization technique. So the agenda for today is to first go over multi-level hypergraph partitioning. Then I'll talk about Bipart, which is a parallel and deterministic hypergraph partitioner, which has three phases: coarsening, initial partitioning, and refinement. And finally, I'll talk about our results and evaluation. So let's start with multi-level method. There are many examples of this method in the real world, such as Metis and Zoltan. It is the most successful partitioning heuristic for partitioning large graphs, and it consists of three phases: coarsening, initial partitioning, and refinement. In coarsening, we iteratively merge nodes of a hypergraph to get a small enough hypergraph where we can run an initial partitioning on that. From there, we go back to the original size hypergraph while running a refinement algorithm on these partitions to refine the partitions. The first phase is coarsening. Here, the goal is to create a small hypergraph. It helps in successively reducing the size of the hyperedges as well as the nodes. The second phase is initial partitioning. In initial partitioning, we can use any direct partitioning algorithm to partition the small hypergraph. An example of this direct algorithm can be BFS, spectral partitioning, and many more. Finally, the third phase is refinement, where we want to refine the edge cut. Any iterative improvement algorithm such as KL or FM can be used in this phase. Now let's go and talk about Bipart, which is a parallel and deterministic hypergraph partitioner. Our main contribution is to introduce Bipart, which is an open source framework for deterministic parallel multi-level hypergraph partitioning. We will introduce a novel deterministic parallel coarsening strategy, and finally, I'll introduce a novel deterministic parallel refinement strategy. So let's start with the parallel deterministic coarsening. Coarsening in hypergraph can be described using the idea of matching from graph theory. We have node matching. Node matching of a hypergraph is a set of node pairs U and V, where U and V belong to the same hyperedge, such that node pairs have a node in common. For example, the node matching of this hypergraph is EG, FH, AC, and BD. We have hyperedge matching. A hyperedge matching of a hypergraph is a set of hyperedges such that no two of them have a node in common. For example, hyperedges 2 and 6 are a hyperedge matching. In Bipart, we use a novel multi-node matching. A novel multi-node matching is the partition of nodes of a hypergraph such that each set contains nodes belonging to only one hyperedge. A multi-node matching of this hypergraph can be FGH, BCD, and AE. And another multi-node matching can be ACE, BD, and FGH. In general, we have many multi-node matching of a hypergraph, and it is important in this problem to always get one multi-node matching. Now let's go and see how Bipart achieved this. So in Bipart, we assign a unique key for all the hyperedges. This key has two components. One is the hyperedge degree, and one is the hash of the hyperedge ID. And hyperedges with larger degree have larger keys. And once we have this key, then we assign each node to its hyperedge with the largest key. So for example, on this hypergraph, hyperedge 2 is degree of 3, and its hash of ID is 4, so that it has the largest key amongst the other hyperedges. The node that is connected to hyperedge 2, for example, BCD, will be assigned to hyperedge 2 because it has the largest key. Here's an example how this parallel deterministic coarsening works in Bipart. Well, first we find this unique key for each hyperedges. The unique key is basically has two components: the degree of the hyperedge and a hash of its ID. Once we find this key for each hyperedges, we assign nodes of that of all the hyperedges based on this key. So the node will be assigned to the hyperedges with the largest key. So for example, BCD will be assigned to hyperedge 2 because that has the largest key. Nodes E and F will be assigned to hyperedge 1, and nodes G and H will be assigned to hyperedge 6, and node A will be assigned to hyperedge 3. Once we find this assignment, the nodes that have the same are assigned to the same hyperedge will be merged together. And for example, BCD will be merged together, EF will be merged together, and so on. On the right, we have this coarser hypergraph that we obtained from the left hypergraph. As you can see, the number of nodes in this hypergraph is less than the original one. And also the number of hyperedges is reduced. Basically, we don't have hyperedge 2 in this hypergraph. The reason is that all the nodes in this hyperedge 2 are merged together. So we don't need to copy this hyperedge to the coarser hypergraph anymore. Next phase is the initial partitioning. The goal here is to obtain a good bipartition of the coarser's graph. And here we use a greedy graph growing algorithm to obtain this good bipartition. In this algorithm, we first start putting all the nodes in one partition, let's say partition 0. Then we compute the move gain values for each of our nodes. This gain basically tells us how the edge card will improve if we move that node to the other partition. Then we pick the node that has the highest gain and move it to the growing partition, let's say partition 1. We update the gain value of all the nodes that share hyperedge with that node, and we repeat this algorithm until the balance is achieved. Basically, if half of the nodes are in partition 1 and half of the nodes are in partition 0. The next phase is parallel refinement. The goal here is to minimize the size of the cut. The approach we take is to use a FM heuristic to refine the partitions. The challenge is that the FM algorithm makes individual moves, so we have to use a variant of FM in order to have to move a few nodes in parallel. And we only move nodes that have high gain values. So let's start with our FM algorithm and see how that works. FM is an iterative improvement algorithm, and it only moves a single node at a time to another partition. The way that it decides to move nodes is to using this gain value. And the way that we compute this gain is by running this formula Fs minus Te, where Fs is the number of hyperedge cuts that connect to node I, and Te is the number of uncut hyperedges that connect to node I. For example, the node C here is connected to 3 hyperedges, the green and the red and the blue. In the green hyperedge, C is the only node in the other partition compared to its neighboring node. So if we move C to the other partition, we will improve the edge cut by 1. On the other hand, on the red hyperedge, C, E, and A are all in one partition. So if we move C to the other partition, we will increase the edge cut by 1. So at the end of the day, there's no point in moving C to the other partition. Whereas for node E, all these neighboring nodes, for example, G in hyperedge brown and C and A in hyperedge red, are in the same partition. So if we move to E to the other partition, we will increase the edge cut by 2. So it's not a good idea to move node E to the other partition. Now let's look at our refinement algorithm. So refinement algorithm is an iterative algorithm, and in each step, we project the bipartition of the courses graph to a finite graph. And for each iteration of the refinement, we first compute the gain value for all the nodes in our bipartition, and we create 2 sets, L0 and L1. In L0 contains all the nodes in partition 0 that have gain value larger than 0. L1 contains all the nodes in partition 1 that have gain value larger than 0. We sort this node to make sure that our algorithm is deterministic. And once we have sorted this list, we swap this list together. So basically, all the nodes in set L0 will go to partition 1, and all the nodes in set L1 will go to partition 0. Once we've done that, we check if the balance criteria is satisfied or not. If it's not, then we move the highest gain value nodes from the larger partition to the other partition, and we keep doing this until the balance is there. All right, now let's go over the results and evaluation. We implemented Bipart in Galois system, and we compare Bipart with Zoltan, K-Hyper, and Hype. Zoltan is a parallel algorithm. K-Hyper and Hype are serial. We use a machine running on CentOS 7 with 4 sockets of 14 core and Intel Xeon Gold and 187 gigabyte of RAM. All of our inputs are obtained from real-world problems, such as from basically University of Florida sparse matrix collection, Sandia Lab, and SAT competitions. 2 of our largest graph, random 15 million and random 10 million, are randomly generated to make sure that we have very large hypergraphs as well. Here are results. So we have 2 columns, one column showing the runtime and another column showing the edge cut. The runtime is in second, and as you can see, Bipart was able to partition all this hypergraph And if we compare Bipart to Zoltan, so Zoltan failed to partition the largest hypergraph, random 15 million. And on all the other hyperedges that it was able to partition, Bipart is always faster. The H-code, however, and on some hypergraphs, Bipart is better, on some Zoltan is better. For example, for the two of the largest hypergraph that Zoltan was able to run, random 10 million and WB, the H-code of Bipart is better than Zoltan. However, on NLPK, Zoltan is doing better. Compared to hype, Bipart is always faster and creates better partition for all these hypergraphs in this example. But hype was also able to partition all of these hypergraphs, even though it took more than an hour to partition 2 of them. For Car-Hyper, Bipart is always faster on all the hyperedges that Car-Hyper was able to run. And specifically, the largest one that Car-Hyper was able to run, WB, Bipart is about 70 times faster. Car-Hyper failed to run to partition 2 of our hypergraphs. And but on the ones that it was able to run, it's roughly slightly better than Bipart in terms of the H-cut. Let's look at the scalability of Bipart. So we are scaling up to 7x for the larger hypergraphs and about to 2x for the smaller hypergraphs. Here results for Kv partitioning. We chose 2 of our hypergraphs to run this Kv on IBM 18 and WB, which is a larger hypergraph. So we compare our results only with Car-Hyper because Zoltan is not deterministic and hype is always producing worse results in terms of both runtime and quality compared to Bipart. So both Car-Hyper and Bipart were able to partition IBM 18 on 2, 4, 8, and 16 partition. And so Bipart is always producing better, faster partitions, whereas Car-Hyper is better in terms of quality. However, on the larger hypergraph WB, Car-Hyper was only able to partition this hypergraph on k equals to 2, and for larger number of partitions, it failed to partition WB. Here we are showing our parallel Kv partitioning. So Bipart uses a parallel recursive bisection to do to achieve Kv partitioning, and this figure shows that the time of computing Kv partition for these 2 largest hypergraph is scales with the time it takes to do a 2 partition, which is what we expected. And so basically, if k is the number of partitions, the runtime of Bipart increases by the log of the log 2 of the k. Thank you very much to listening to this talk. You can download Bipart from this URL and feel free to email us if you have more questions. Thank you.